spend as much time as possible, so I'm happy to introduce Sam, our University of Bristol, to talk about convergence bounds for the random walk Metropolis algorithm.
Thanks, Joris, and thanks to the organizers for the invitation to speak here. I'm going to speak about some work that we've done in Bristol over the past couple of years. All of it is joint with these three. So Christoph and Andy are here this week. Anthony, unfortunately, is not, but also contributed massively to this work. Okay, so there's a few papers that are getting involved here. So we had this sort of technical report at some stage covering lots of things about Markov chains, sort of targeted towards the random walk Metropolis. The first fruit of this project was this published paper here on the random walk Metropolis algorithm, which has been published. And then we have a sort of follow-up paper, which we're revising at the moment. And if we're lucky, we will have a revision online by Christmas, let's say. So, keep space under the Christmas tree. Right. So there's a few things to talk about today, but based on the title, the two main things are this algorithm called the random walk Metropolis, and this other concept called Isoperimetry. And maybe for this audience, the second one is perhaps a little bit less familiar, so I'll just give a few sneak peeks of it before talking about Markov chains properly. Okay, so some very quick ones. And so for people who've done an undergraduate maths degree, this is a sort of almost counterexample thing that one often sees in the first couple of years. So what this is, it's called Gabriel's horn or Torricelli's trumpet. What it is you take the curve y equals 1 over x, you rotate it around the axis, and you form the surface of revolution. And so the reason this is sort of interesting to show to undergrads is it's something where you can compute that the volume inside this trumpet is finite, but the surface area is infinite, okay? And so when you see this for the first time, it seems a little bit shocking. It's sort of a mismatch of expectations in a way. But it's something to sit with for a bit. And one thing we'll come around to later is that this sort of behavior of having a very large surface area whilst having a very small area is actually quite easy to achieve. It's somehow generic. The other direction is the interesting one. Okay, so this is one thing to sit with for a bit. So we have some relationship between surface area and volume that is of interest, right? So another one, this is something from antiquity called Dido's problem. So this is something that's written about in the Aeneid. And so the idea was in this story, so Dido was, I think, the daughter of the king of Phoenicia or something like this, had been exiled from her kingdom and was sort of on the run looking to make a start over of things. And so she was in sort of North Africa, I think, and found a friend and was looking to set up some land for herself. And so she had a bull's hide with her or something like this and said, look, just give me as much land as I can enclose with this bull's hide, we'll be fine. And the guy said, okay, this sounds like a good deal. And so what she did, the first thing was to take this sort of 2D object and sort of cut it very finely into one very long piece of string. And then, to sort of be ambitious, she said, how much of an area can I impose with this sort of synthetic string subject to this boundary? And so what we see here is, that she sort of, this here is the shore, basically, the sort of north coast of Africa, I think, enclosed a large sort of arc of a circle to get as much area as she could, and that's where the city of Carthage was founded, at least nominally. I don't know how serious these stories are, right? But again, we have this... Perfect. Yeah. So we're in a situation, again, where there's some sort of perimeter which is being constrained, and we want to maximize area. So there's the sort of same relation. Okay, and then the third one is a little bit more synthetic, but I thought it would be nice to connect things back to Markov chains quickly. So suppose I have a Brownian motion evolving on the sphere, okay, for as long as you like, right? And so suppose I say, look, I want you to mark out some territory on this sphere that will see the Brownian motion very often, and you're only allowed to take up a certain amount of mass, okay? And so that's not a very interesting problem, because sort of by the ergodicity of the process, for any amount of, if you say it's going to have mass 1/4, then you will pass through it sort of equally frequently in all cases. But suppose I narrow things slightly and I say, okay, you're going to look at this Brownian motion, sampled at some high frequency time interval, and what I want is not just that it often lands in the set, but that it often lands in the set and stays there. Okay, so over sort of adjacent timestamps, you're sort of in there and staying as often as possible. Okay, and this one is not as obviously related to the first problem, but somehow still here I'm giving you this area constraint, and I'm saying how can I trap a Markov chain inside of a set somehow? And we'll see eventually that this is quite closely related to some notion of perimeter, and we will come back to this later. But these are just some sort of snippets of, when I talk about isoperimetry, these are the sorts of things that are going on. You have some relationship between a notion of mass and boundary mass, and controlling the sort of inequalities between them in an interesting way. Okay, and then from here we sort of jumpstart into MCMC stuff, but this will hopefully be useful to build on later. Okay, so it's sort of an audience where this doesn't need so much discussion, but I want to set notation and sort of intuition here. So, the thrust of what I'm talking about is the endeavor of Markov chain Monte Carlo, whereby we have some target distribution pi, let's say on RD for today, right? And I want samples from pi so that I can answer questions. In my community, they're often statistical questions, but for someone else, they could be thermodynamic questions or otherwise, right? And so this can often be very challenging. And so the thrust of MCMC is, instead of trying to very carefully construct an exact sample, I'm going to iteratively refine a sample to get something approximate. Start with something okay, get something better and better and better, until after a certain number of iterations, I'm happy with what I have. And practically speaking, we want that number of iterations to be small or controllable, right? We can't wait all day necessarily. So here's the schematic, right? I have my initial sample x0, and let's say everything's time homogeneous and simple, right? I have a Markov kernel which takes me from x0 to x1, then to x2, and so on. For some large capital N, I have a sample which is appropriately distributed, and then I use it to compute integrals and so on. Okay, I won't sort of linger on this, but I think it's healthy to remind ourselves of why we're doing it. Okay, so to make this practical, we need some way of constructing these Markov kernels. And I think driven by applications, we like to come up with very generic ways of constructing Markov kernels that perhaps don't depend too much on the fine details of the distribution. That's sort of driven by how they're used. So one generic recipe for constructing a Markov kernel P, which is pi reversible and hence invariant, here's a principle, right? So start with some measure nu, not necessarily a probability measure, which dominates pi, so something which agrees on what things are possible, if you like. And suppose that this nu is simple enough that we already know some reversible kernel Q, something that sort of says, okay, we know what space we're interested in and we have some means of exploring it with a bit of structure. So I'm going to write var pi here for the density between the distributions. And so what is a Metropolis algorithm given these ingredients? So not a Metropolis Hastings, the sort of distinction is a little bit meaningful. So what am I going to do? At location x, I propose a move drawn from Q, and then I evaluate the move using this ratio of densities. And based on that, I decide to go there or not, okay? And the key thing is sort of it only depends on these ratios here. The sort of dependence on the proposal kernel Q essentially vanishes, which is structurally a bit nice. With this probability, specifically the minimum of 1 with this ratio, we make the move, otherwise we do not, okay? This will be familiar to many, many people, but I want to be explicit about this notion of a Metropolis kernel. Okay, so that's still very generic. Let's get down to the random, let's give the schematic here. So at the start of the day, we have this measure nu and some kernel which leaves it reversible. We move to pi by looking at its sort of density. We sort of restrict this guy in some sense. And then using that, we construct some acceptance function alpha, which gives us this kernel p, which is then pi reversible. Okay, that's sort of the ingredients that go into it. Okay, and so one of the simplest things you can do in this world is to, as I said, we're working with distributions that have a density on RD. And so I'm going to say, okay, well, I know if I have a density, I can take the reference measure to be the Lebesgue measure. And what's the simplest way to leave the Lebesgue measure invariant that doesn't involve doing nothing at all is a random walk. And for me, it's convenient to be a Gaussian one, but it's not structurally very important, let's say. And so what we do, at our current location, we sprinkle a bit of Gaussian noise on top, and we accept our move with this probability. And I'm going to sort of informally refer to this kernel as RWM pi sigma squared for the random walk Metropolis kernel with invariant measure pi and proposal variance sigma squared. And, for practical reasons, why is this interesting? It really doesn't make very strong assumptions about the target that you want to apply it to, right? As long as you can evaluate this pi up to a constant and generate Gaussian noise, you're in business. And somehow, if you can't do either of those things, you're in a pretty challenging case, right? Okay, so let's talk a little bit about this random walk Metropolis kernel and say what are some sort of qualitative things that we know about it. Okay, so I'd say under almost no conditions, this genuinely gives you a pi reversible kernel. If all of the things I've said are well defined so far, then it will follow that we have a reversible kernel. Now, in terms of sort of qualitative description of the long-time behavior of this process, what is true? So under very mild conditions that I won't mention, you have that it's ergodic, that it's fit for purpose, and if you run the chain long enough, you will end up with a genuine approximate sample from pi. So we're fit for purpose. Okay. Now, under an assumption which is sort of that the tails are lighter than exponential and not crazily curved in different ways, and I won't go into that, then we have that we'll be exponentially ergodic. The rate of convergence is sort of exponentially fast with time in total variation, let's say. there's also this additional phenomenon that if we have heavier than exponential tails, that this can't happen, okay? That we're necessarily slower than exponentially ergodic. And the sort of heuristic argument for this is that, you know, your random walk moves at velocity 1 in some sense, or at constant velocity. And so to get out into the tails and then back quickly enough to see the mass that you should can't happen. So there's sort of an immediate bottleneck in what can happen there. You can make that more rigorous if you have deterministically bounded moves, but the same argument sort of goes through. Okay, so these are all sort of qualitative, but they give us an idea of what might be achievable when we want to go quantitative. Now, an interesting feature about the random walk Metropolis, which is often presented in slightly different ways, is say I have my algorithm as I've described it, and I take this step size going to 0 from above, and I rescale time appropriately, we obtain, in some suitable sense, this limiting diffusion to sort of describe the process. Now, this approximation doesn't hold in every possible sense, but if you sort of think, you know, uniformly on compacts and uniformly, you know, up to some fixed time horizon, this holds reasonably well as sigma goes to 0. And this is what we would call the overdamped Langevin diffusion, and throughout this talk I'll sort of abbreviate it as OLD pi. Okay? So people will be familiar with the sort of optimal scaling type results for high dimensional MTMC where you get similar behavior. That's not really what I'm saying here. I'm really saying fix pi and send sigma to 0. You already get this behavior. Okay? This is from sort of the early 90s. And so what's compelling, you know, and I'll sort of describe why this is a nice object to work with momentarily. What's sort of compelling is to say, okay, that's true as sigma goes to 0. If I have some finite sigma that I'm implementing my algorithm with, does it follow that the mixing time, you know, appropriately characterized of my algorithm is essentially that of the continuous time process rescaled by my step size? Okay, that's a sort of optimistic hypothesis that we will try to work towards. So let's talk a little bit about this diffusion. So for us, it'll be useful to write pi in terms of this sort of potential here, because the sort of smoothness properties of the target are nicely characterized in terms of this guy rather than pi itself somehow. Okay, so looking at this process, it's straightforward to check that we again have a pi reversible tensor invariant process, and it will, you know, in the long time limit converge to what we want again. So, you know, we haven't made things dramatically worse, let's say. Yeah, just to, I won't linger on this, I think, but it's a little bit embarrassing that, you know, if I tried to give you an example of a diffusion that is anomalous, I've kind of given you the worst possible example. From the point of view of actually sampling an invariant measure, this is maybe as conventional as it gets. Okay, so let's carry on and just accept that. Okay. Okay, so yeah, as I said, it's somehow canonical, but this means it comes with a sort of a rich understanding, right? So there's a lot of features of a probability measure pi that you can probe, like sort of its geometry in some loose sense, how it interfaces with concentration of measure and optimal transport and things like this, which are naturally probed by studying this diffusion process. Okay, you can sort of learn quite a lot about it from that. And so various aspects of it are well understood by now, and I'll be a bit more precise about that momentarily. Okay. So here's a crash course on the long time behavior, just to give an intuition of what we might be aiming for. Okay, so all the convergence here described is in an L2 sense. I was initially a bit worried about describing it this way, but this is what Gabriel was talking about in his talk just before lunch, right? Measuring things in sort of a Hilbert space way. Okay, so what is true about the overdamped Langevin diffusion? So if our potential is convex, then we know that the convergence to equilibrium is exponentially fast. Okay, that's sort of true generically. If it's uniformly convex, in the sense of having a Hessian that's uniformly bounded away from 0, then actually you have something stronger. You have sort of initially a convergence that is faster than exponential. Okay? You can view this as sort of exponential convergence in a different metric if you like, but because I'm going to talk in an L2 way today, this is sort of an accurate description. On the other side, if we have a U which grows sublinearly, so we have sort of heavier than exponential tails, then the convergence must be slower than exponential. In a way, this follows from what I said about the random walk already. And finally, so something which is conjectural but pretty close to true at this stage, is that actually if U is convex, the rate of exponential convergence is conjecturally dimension-free, in the sense that if I have a log concave measure and I reshape it to be isotropic, right, the covariance matrix is the identity, then the rate of exponential convergence is a constant, which doesn't depend on anything. Currently, this is proven up to a square root log d factor. Okay, so mathematically, it's not true, but in terms of giving complexity bounds on algorithms, you know, if you're going to complain about square root log d, that's a conversation to have another time, I think, right? So it's a sort of nice process in that sense. And so, okay, these are the sort of cases where things are particularly well understood. There's also various transfer principles that let you infer things about distributions that don't fall exactly into one of these categories. Okay? So if I have a density that's very nice and the diffusion converges very quickly here, and I multiply that density by something that's bounded away from 0 and away from infinity, still the diffusion will converge very quickly, and the rate will be changed by somehow the maximum divided by the minimum. Okay? There's also things like Lipschitz transport. So, if I have a probability measure which is sort of not log concave, but I can get it as a transport image of something log concave with good Lipschitz constant, then we inherit stuff from that as well. And so, in practice, when you're studying a given target, you sort of check the first 4 things first, and if you're not in those categories, you might try one of these things as a first port of call. And then it's sort of, if you don't fall into those categories, you have to work a bit harder. Okay, so the point of this is to say, if we want to study the convergence of this process, that's something where I can open up papers and books and get a reasonably good idea of what's known, right? Okay, so connecting the random walk to this diffusion. So as I sort of alluded to, there is some strong resemblance between these processes. And so what we sort of hope to be the case is that, if I'm running my random walk Metropolis algorithm and I'm accepting moves reasonably frequently, I'm not getting badly stuck, then we would hope that the mixing time is really controlled in this sort of a way, that we're slowed down by having to use the finite step spies, but there's no real obstruction to convergence otherwise. Okay? And so to try to make this rigorous, you need to say what kind of resemblance you want to hold. Okay? And so a natural thing to ask for would be something like pathwise behavior, to say, okay, I have these 2 processes, maybe I can show that they stay together uniformly in time in some very nice way. And as far as I know, this is not quite true, and it would be quite hard to turn it into a real convergence proof that would get you the right rates, and so on. In a sense, the issue is that when you're out in the tails for something that sort of has superlinear growth, right, the diffusion is moving very fast with sort of velocity much greater than 1, and your little random walk is sort of slowly moving O of 1 per step. Okay, so this is to be contrasted with, I think, sort of things like the unjusted Langevin algorithm. That sort of an argument might actually work. But for random walk Metropolis, as far as I know, it's not going to. But there is a key notion in which the 2 processes are similar, which is in terms of their exit behavior or their boundary behavior. So if I start each of the processes in some set, and I say, how long is it going to take them to get out of that set, that behavior is sort of largely analogous, up to some strange edge cases, let's say. Okay, so this is sort of going to connect us back to some previous notions. Right, so back to isoperimetry. Right, so I'm going to talk about something called the R enlargement of a set and the Minkowski content of a set. So roughly speaking, we're going to need to say, okay, if I take a set and I look at all of the points that are within a certain radius of that set, I get something called the enlargement of that set. Right, so here, if we think of this blue box as being our initial set, then the interior of this rounded red object is the sort of 1 enlargement, if this distance is 1. Right?
And that's in what?
Just in the Euclidean distance.
Measure in space.
So yeah, you have the set, and then you say, look at all of the points where you can find a point in that set where you're within this distance of it. And I'll give you a definition in a second. Okay. So taking A to be some set of interest, let A upscript R be the set of points that are within a distance R of A. Okay. And so now we're going to say, okay, look at the amount of mass in this sort of boundary layer that we've introduced, A of R minus A. You can sort of convince yourself that as R goes to 0, this should be behaving linearly with the enlargement. Okay?
In any dimension, we are in 2 dimensions.
In any dimension, yeah. It takes a moment, but when you think of a set that already starts with positive mass and how you increase it, this is what we expect. Yes, okay. And so this is sort of what's called the Minkowski content of the set A under the probability measure pi, right? And we'll write pi plus for that. So that's our notion of perimeter or surface area as relevant to probability measures. Okay? And so relating back to the original isoperimetric problem, what do we want to do? We want to control this boundary in terms of the mass of the set. Okay? And so we're going to write I of pi, or just I, to be the maximal function such that for any possible mass, if I know the mass of the set, then I can lower bound its boundary. Okay? So this guy I is the isoperimetric profile of pi, and it is going to be completely central for what comes later. Okay? So, under a probability measure, if I enlarge the set a little bit, how much can its mass increase by? That's what we're going to care about. So yeah, as I say, the way it's going to be used is we'll make statements of the form, if the mass is this, then the boundary is at least this. Okay, and a sort of tough exercise to sit with for a bit, which I was not very good at when I first learned about this stuff, is to think about what sort of sets A are going to be extremal in this inequality. What's going to sort of make it saturate. So in these initial problems from the start of the talk, right? If you have a piece of string and you want to enclose the largest possible area, you put it into a circle, right? People might be familiar with this. For probability measures in general, particularly those with sort of infinite support, it's a bit less obvious what the extremal sets are going to be. And I might come back to that later. Okay, cool. So these are some definitions, and they'll be useful for us. Right, so let's give some examples of what this function looks like. So start off thinking in 1D, okay? So let's look at a double exponential distribution or Laplace distribution. In this case, the isoperimetric profile is exactly linear, actually. I forget the constant. But what's happening here is essentially, you have this density like this, and you say, I want to find a set that has a given mass with a very small boundary. The trick is, you might think it's natural to start by thinking about an interval, and as you shrink an interval further and further to the right, there's no boundary on the left anymore. And so you might think that you've won something there. And so the only boundary is sort of what's happening at the right. Okay, and if you look at the sort of, say I look at the set t infinity, that has mass e to the minus t up to a constant, and at the boundary it has density e to the minus t as well. So the boundary is comparable to the size of the set, so the isoperimetric profile is linear. Okay. Now, for Gaussian type targets, we get something a bit better, actually. So the extremal sets are again these half spaces on the tails. Okay, but we see that we actually have a much larger boundary when p goes to 0. Okay, so when you're looking out at these tails, if you have a certain mass, your boundary might be bigger in relative terms. Okay, and if I take these sort of Subotan type distributions in between, where this alpha is between 1 and 2, we get this formula that interpolates between the two. And again, the half spaces are extremal. So it's sort of a general thing that in one dimension with symmetric log concave distributions, the extremal sets are the half spaces. Okay. This is in a monograph by Bobkov and Huderet from the 90s. Okay, so that's all in one dimension. But actually, if I take IID products of these guys into dimension D, the same thing is true. I pick up a little factor in front, but it's not dimensional, and so we're in good shape. So I can already study products of these in arbitrary dimension and say how nice they are. If alpha is greater than 2, some funky things happen because somehow if things are better than Gaussian, they can't stay arbitrarily better than Gaussian when I tensorize them because of the central limit theorem. Okay, you'll eventually see that in a lot of directions things look Gaussian, and so, okay, that's not allowed. But yeah, the key thing to note here is that for small sets, the behavior can be much better, right? You can have very large boundary for very small sets, and going to sort of the Markov chain perspective on things, that means that when you're out in the tails, you get out of them very quickly. Somehow. They're very easy to escape, those sets. Okay, so now some other examples. So let's look at heavy-tailed problems instead. Okay, the model problems sort of change a little bit. So let alpha now be between 0 and 1. So I'm no longer log concave, but I'm still sort of not crazily heavy-tailed. In this case, so we get the similar sort of p times log 1 over p to the 1 minus 1 over alpha sort of thing here, but we do pick up an extra dimensional factor on the inside, right? And so what this means is that, even though the level sets of x to the alpha themselves don't look crazy, when you start looking at the level sets of the sums of these guys, for example, they become more and more non-convex and very strange, and the bad sets sort of look worse and worse. And similarly, if I take a sort of spherically symmetric version of the same problem, I'm going to get the same behavior, but I'll pick up a dimensional constant out the front in general. Okay, so here, things get a little bit worse with the dimension, but again, log factors, it might not be terrible. When we start looking at sort of polynomial tails, we get even more dramatic effects here. So now eta is just positive, let's say. I take a product of symmetric Pareto distributions, as you like. And so now we have sort of a polynomial factor in P and a polynomial factor in D penalizing us. Okay, so things are getting quite a bit worse. And there's a similar case, when things are spherically symmetric. Here, the challenge is now that for small sets, the boundaries are tiny. Okay, and this is because when you have heavy tails, you can have small sets that are just right out, off in the distance, for which the density there is very small. Essentially, it's a good exercise to sort of do by hand in the polynomial case, I would say. Moreover, tensorization makes things worse. Okay, in the convex case, I could take products of nice things and get something nice, whereas here, sometimes you can think of it as every time I add in another non-convex things, that's another problem for me to worry about somehow. Okay. So just to give a brief overview of how you actually obtain these estimates. So as I said, in one dimension with suitable sort of symmetry assumptions and so on, the picture is rather complete. So this monograph of Bobkov and Houdray that does a pretty solid analysis of this symmetric case. I won't go into it, but in a way the asymmetric case is not much harder because one of the two sides is going to be easier than the other and you sort of restrict to that case. There's some sort of generic techniques based on Lyapunov conditions, sort of cultivated by these four and some co-authors over a series of papers, which are very good at getting the right rate of how things behave as this set size p changes, but usually in terms of the constants it's not quite as good. It's what people who've worked with Lyapunov conditions in general might expect, let's say. As I said before, in the same way that for the convergence of the Langevin diffusion, there's transfer principles, here there are again transfer principles, and they're often the same ones. Okay, so this is kind of generic stuff, if you like. And now if I restrict to the case of convex potentials U, I have that the profile is tensorized nicely. So what that means essentially is that if I take a product of log concave things and I know the isoperimetric profile for each of them, then the isoperimetric profile of the product, it's just the worst of these guys, basically, up to a constant. So you don't get any extra issues in that sense. Moreover, if you have a convex U, then there's a very close relationship between the isoperimetric profile and different functional inequalities. So people here who've looked at log Sobolev inequalities, Poincare inequalities, and so on, there's a nice way of translating between the two of them in a way that doesn't lose dimensional constants. Okay? So there's many ways of saying that a probability measure is nice somehow, and under convexity they more or less translate into one another quite nicely. This is sort of a big contribution of Millman in particular. Okay, so let's hopefully get back to random walk. Yes, okay, so here's something to say. So I would say when I first saw the definition of the isoperimetric profile, it has a very static feel to it, right? You're saying find a set of a certain mass that has a boundary of a certain size. Okay? There's no dynamics there a priori. But it is true that you can reinterpret the isoperimetric profile in terms of dynamics as follows. And it's sort of related to this third example I gave at the start. So say I draw x naught from this distribution pi confined to a set A. Okay? And let's say I let it evolve for a very short amount of time. Okay? What is the probability that I escape that set over a very short time? Okay, and if you think about it for a moment, right? If I'm in a set and I want to escape it over a short period of time, I have to more or less be at the boundary already. And because of sort of diffusive scaling, you don't really have to look at the drift because it's going to be order t. The diffusion is order t to the half. And so the question is really, if I'm on the boundary of a set, what's the chance I have for a Brownian motion to kick me over the boundary? Okay, that's all we see there. And so in a way, that's the dynamical interpretation of isoperimetry, is how difficult is it to escape sets on short time scales, and then there's sort of ways of extrapolating that to long time scales.
So this parameter R that you had is just maybe can be interpreted in a number of steps of a Markov chain.
Yes, exactly. Yeah. Or somehow like the t or the square root of t, this kind of a thing. Yeah, and so from this point of view, you can say, okay, isoperimetry, it's this sort of classical, very geometric problem, but if you like, you can also view it as a way of characterizing the difficulty for a diffusion, or perhaps a more general Markov process, to escape a given set. Okay? And so the intuition you should have is that if it's easy to escape every set, then mixing must be fast. Okay? And if there are some sets that are very difficult to escape, then you will get slowed down and have much slower convergence. Okay? And this is what we eventually will see.
There's also the diameter, right? I mean, you are interested in perimeter, but there's also the diameter of.
Yeah, so it potentially does. For the sort of analysis I do, we don't see it. But I would imagine there's refinements where you can look at these things as well. Okay, so say I've worked very hard and I find the isoperimetric profile of a probability measure. Under some fairly reasonable conditions, one can show that the mixing time of the continuous time process to an error epsilon can be characterized in terms of this integral here. Right? So it involves the isoperimetric profile downstairs. And this delta naught here is a factor that relates to the initialization of the process. And we don't need to get into that just yet, but it can be quite big. Okay? So the rate at which we converge is going to be dictated by the behavior of I pi as p goes to 0. How difficult is it to escape small sets? Okay? How badly trapped can we get? What's a bit nice and quite rare in this area, I would say, is that this sort of gives you a unified description for cases where you have exponential rates, faster than exponential rates, slower than exponential rates. You get a similar formula in each case. The definition of the delta naught changes mildly in one of them. But yeah, the key thing is that these rates, they're dictated by the behavior of I pi as p goes to 0. in terms of how much you see the effect of initialization, let's say. Okay, so right, let's go back to the random walk metropolis and see what we can say. So we've seen that doing a sort of isoperimetric analysis of a probability measure gives us a lot of information about the convergence of this diffusion. And so optimistically, we might want to ask, can it also be informative about how our practical algorithm converges? So then we have theorems, then we have guarantees, and we're sort of happy at that stage. Now, the expectation would be that it shouldn't work directly, because we need to use the discreteness of the process at some level and account for the fact that we're taking a finite step size and so on. And we'll see that sort of with one extra ingredient, this is essentially the only other obstacle to proving a result like we want. Okay, and so I'll make that precise. Okay, and so this is the extra ingredient that we need to look at for the sort of discrete time formulation. And so what it is, so let delta be greater than 0, being a sort of distance, right? And it's fixed. I'm not sending it to 0. It's really fixed. And for some threshold tau, say that the Markov kernel P is delta tau close coupling if we have this condition, right? Which is that if I have 2 points x and y that are within delta of one another, then the total variation distance between the Markov kernels is bounded well away from 1. Right, and so the interpretation is, as I say here, if we get 2 copies of the chain within delta of one another, we can couple them to make them meet exactly in one step with a decent probability. Okay, so yeah, just emphasize, this is not a for all epsilon there exists delta sort of thing. It's really fixed tau, fixed delta, prove this, and then carry on. But indeed, it's still morally a sort of continuity condition about the kernel, that when you move the x's, things don't change crazily. And the point of that is, proving something like this is a bit easier than proving the full continuity, let's say. Okay, so here's a general proposition which, we write something a bit like this. It's sort of known a bit in some forms from work of Lovaas and Van Palle, let's say. So this is not specifically about random walk metropolis. I'm just saying let pi be a probability measure with a known isoperimetric profile, and let p be a pi-reversible Markov kernel which satisfies this close coupling condition and some other technical stuff that I won't go into. In this case, the mixing time of that Markov kernel can indeed be bounded in terms of this integral that we saw before, slowed down by a factor that depends on this parameter delta, which is something like a step size, and this sort of coupling probability tau. Okay, and all of the constants that I'm hiding in here are fully explicit and they're less than 1,000, let's say. Okay, and so just to comment, so in practice, we are very rarely interested in sending tau to 0. You should think of it as being a quarter or something like this. Okay, there are some sort of interesting cases of processes concentrating near a manifold or so on, where it is interesting to send tau to 0, but it's relatively rare and it won't be coming up in what I do today. Okay, so can we establish this for the random walk metropolis? Okay, can I show that if I have my random walk metropolis, I have 2 points that are within about sigma of one another, can I make them meet in one step with a decent probability? Okay, and so we do this in a couple of steps, which are largely elementary, but I think quite nice. So the first step is that for any metropolis kernel, we can bound the total variation distance between the kernels in terms of the total variation distance between the proposals and the worst case rejection rate out of any state. Okay, and I'll be slightly more precise about that in a second. And the intuition here is, if I want to couple these guys, I need to propose the same thing first, more or less. And then once I'm at that stage, I just need to make them both accept. Okay, and because it's sort of metropolis type, there's a way of decoupling these acceptance decisions, which is harder for general metropolis Hastings kernels. So that's nice. So okay, we want to bound this guy away from 1, so we can control this thing and try and bound this thing as well. Now, in the case where Q is this specific, normal random walk, using sort of elementary techniques, you can just explicitly bound this total variation distance as being approximately linear with the distance scaled by the diffusion constant. Okay, for if people are interested in the technical details, you just bound the KL divergence explicitly and you use Pinska's inequality. So it's a really explicit calculation. Okay, and so the takeaway from this is that if we want to establish the close coupling condition, it's going to be sufficient for us to say, okay, I'll take my delta to be, order sigma, make this term small enough, and then bound the worst case acceptance rate away from 0. Okay? So this is what I was saying before, you know, if you have a nice enough process and you're accepting things most of the time, probably everything is fine and you do basically look like the diffusion in terms of mixing behavior. Okay, so let's have a look at the acceptance rate, right? So I'm going to define alpha of x to be the acceptance rate out of the state x. So averaged over the proposals, what is the acceptance rate there? And we can write it like this way, which is very similar to what Werner had written this morning, right? So we have the change in the potential, and we want to show that this thing is bounded well away from zero, uniformly in where we start, okay? And so if we want to do this, you know, writing it this way, it's quite natural to make some sort of, you know, modulus of continuity assumption on U so that we can control this guy nicely. Okay. I'll show you how we go about that. So assume that we have some symmetric function psi for which, you know, if I look at how the function U changes when I perturb it by some h, that it's upper bounded by the tangent plus this error term psi. Okay? And in most cases, it's fine to think of this psi of h as being something like the norm of h squared times some smoothness constant. But you know, for this result, you can be as general as you like. And under only this assumption, you can lower bound the acceptance rate uniformly in x by half times the exponential of this negative Gaussian expectation. And for this type of psi you would see in practice, this is something you can, you know, evaluate very explicitly. And so once you have this expression, what do? You pick a specific sigma, which should depend a little bit on the dimension and this specific psi, to stabilize this quantity as being at least a quarter, let's say, but certainly away from zero. And the point is that this is very easy in practice. For the specific psi's that you would work with, that's an explicit computation you can, you know, give to anyone. Okay, and so now we have all we need to actually analyze the random Metropolis itself, right? So there's a nice division of labor that comes up here, where if you want to do this, there's two steps. You write down pi, and then you get one friend to look at the literature and study the isoperimetric profile of pi, and they give you this function, okay? And then that's their job done. You don't need anything more from them. Okay, and then you get another friend who's, you know, maybe they're doing optimization or non-smooth analysis. You get them to study the smoothness of U, and then, you know, using this construction on the previous page, you get them to tune the step size so that the acceptance rate is bounded away from zero. Okay, and that's something they'll be very well set up to do. So, you know, you have your probabilist or geometer up here and your optimizer down here. They give you your answers, you combine them, you get a mixing time like this, and it's a, you know, an honest theorem. This is all, you know, true up to constants that I can tell you in principle. And so we've sort of delivered on what we wanted to be true, that by studying the continuous time process and controlling the acceptance rates a little bit, we actually see what's going on. Okay? Maybe one point I can make is that these are upper bounds. Sometimes they are sharp, sometimes they are not. But often they are very accurate, let's say. Okay, let's click through.
So having the upper bound is already something fantastic.
Yes, yeah, exactly. But so the reason I say that is, in some sense, what I want to say is the mixing times of the two processes are comparable in exactly this way, whereas all I'm technically saying is the upper bounds on their mixing times is comparable in this way. But I more or less believe it, let's say. Okay, so I'll give a few examples here of sort of model problems where we can understand what's going on reasonably well. So one is sort of a pretty conventional thing to look at in the literature, which would be the well-conditioned convex function case. So what we're saying here is that there are some constants, little m and big L, such that if I look at any location in space, I can compute the Hessian of U, and its eigenvalues are bounded well away from zero and infinity with these constants. Okay? You can sort of phrase this in different ways, but I'm happy to write it this way. So under these conditions, you can write that the isoperimetric profile of this pi is bounded below in this way. And what is this? This is basically saying, from the isoperimetric point of view, it's as good as a Gaussian with variance 1 over m. Okay? With no dimension. You know? And you know, under this sort of smoothness condition on the L, we can indeed get this psi of h to be L over 2 times h squared. Very explicit. If you want to compute that Gaussian integral from before, it's, you know, just what is the variance of a Gaussian distribution. You can handle it. Okay, and so under these circumstances, if you take the step size, the proposal standard deviation to scale like the Lipschitz constant times the dimension to the -1/2, you get a mixing time like this, where I've sort of ignored the initialization there, but it's not a problem, let's say. Okay, and so this kappa here is the sort of condition number of the process, which tells you how poorly scaled things are. And so you can look at it two ways. You can say, okay, what are the two things that impede mixing? Well, in discrete time, it's how well scaled the target is, and, you know, this dimensional factor. But you can also split it up differently and say it's two factors, really. One is how well would the continuous time process converge, which is to do with this m, and how much do I have to discretize things to slow things down, which is this LD. Okay, so there's sort of different ways of interpreting it, if you like. Okay, another family of examples that will sort of exhibit some different properties. So I've called these LP type targets. I wouldn't say I believe they're extremely practically interesting, but they're a good way of exposing the assumptions that we're making and how they fit together. Okay, so I'm going to look at potentials that are convex, where what I do is I take the usual LP norm of X and I raise it to some power alpha. Okay, and so it's a useful exercise to show that if you want to stabilize the acceptance rate here, you have to scale the sigma like d to the minus 1 over p, at least for p in the range that I care about. Okay. So in the case of alpha equals p equals 2, that's a Gaussian distribution. We did that on the previous slide. Right? The mixing time is like d. Now, if I keep the sort of spherical symmetry, but I raise you to a power between 1 and 2, I'm making things less well concentrated. You know, we're still log concave, but there's more mass leaking out of the center, let's say. And so in that case, you get a mixing time that's like d to the 2 over alpha. Right? So the sort of concentration is where you're paying the price there. The discretization is as easy as ever, up to a point. But yeah, the concentration is slowing you down. Now, if I go fully, well, almost fully general, let's say, and I let these parameters range between 1 and 2, then I pick up another factor up here, which comes from having to use a smaller step size, essentially, to stabilize the acceptance rates. And so you get this mixing time estimate. Okay? And so the picture, you know, one way of viewing it is you have one factor for the concentration or isoperimetric properties of the target, and one factor for the roughness to do with the discretization of the process. And that's also dimensional in some way. Okay, and then final one, which is in the sort of more recent works, is some applications to heavy-tailed targets. So again, the sort of illustrative model problems to say, you know, where are the issues in mixing coming from in these cases? And so the first two examples are sort of product form distributions. Now, say I have a sort of product of Cauchy's type target here, right? Then I get a mixing time that scales like the dimension times this additional factor raised to the 2 over eta. Okay, so you see that when the tails become lighter and lighter as eta grows, the effect of this term diminishes quite a bit. But it's a bit problematic in some ways that, in general, the ways you can feasibly initialize a distribution will have this delta naught being exponential with the dimension, more or less. And so this term can't really be neglected, whereas in the sort of well-conditioned log concave case, the initialization happens very quickly, if you like. Now, if I take a sort of genuine spherically symmetric case with the same sort of Cauchy type tails, then we get a mixing time which is a little bit better. You know, we have a log factor here absorbing things a little bit with a dimensional factor out the front. And again, the sort of intensity of the tails tells you exactly what the convergence is like. Here, I think this assumption is taking tau to be large enough in some way that things don't become extremely non-smooth near the origin somehow. Okay, I think, sorry, no, I said this wrong, sorry. No, this is not a Cauchy type distribution. This is the sort of exponential power with something between 0 and 1. So yeah, you don't pay as much for the initialization, but it is worse than in the Gaussian case. Yeah, so for the genuine student T case here, with tau being taken large enough, you get a mixing time that is quadratic with the dimension, again times this factor here, which depending on the size of eta will be subdominant or very important, right? And so one part of the picture here, which we had not talked about so much in the past, I guess, is that for heavy-tailed distributions, initialization actually plays a massive role. The mixing is very slow, but is a bit slower somehow, and the local behavior looks more or less the same. But this initial phase of getting out of the tails somehow is dominant. Okay, and so I don't really know many discussions of how to initialize well heavy-tailed sampling problems, but it seems to be more interesting than I might have assumed. Okay, so some sort of takeaways here. So yeah, I introduced these sort of isoperimetric problems for probability measures, which start off feeling like a very static object, but actually there's a lot of dynamical information contained in there as well. And if you understand them well, then you can understand the long-time behavior process as well. Now, we talked about Metropolis algorithms for Markov chain Monte Carlo simulation and how they relate to the Langevin diffusion. And you know, we started with this sort of scaling limit type result, but we actually built up to a non-asymptotic convergence theory where we see that the two things mirror one another. And we get sort of a good analysis of the algorithm in several regimes, light tails, heavy tails, everywhere in between. And so the thing I would take away, somehow for whatever reason you need to study the convergence of random walk Metropolis for an application of your own, is that the global picture of the sampling is driven almost entirely by this isoperimetric profile. Okay? If you want to understand the continuous time process first, that gives you an idea of what you can expect. Okay? And then the local picture is just controlling this acceptance rate, okay? Which you can handle by more or less standard techniques, I would say. Yeah, and this all comes from the smoothness of the potential. There's many different ways of characterizing that, but sort of the formulation I've given is pretty general. So in many cases, you will be able to control the acceptance rate very explicitly, although there are some annoyingly simple cases where I can't do it. Okay, and then I think that's me done. So maybe we can go to questions.
Are there questions?
So a couple of questions. So firstly, when you have heavy tails, would it make sense to try to, rather than having like a diffusion of the underlying, sort of diffusing you with something that's more like a leading process or something that can very quickly sort of reach out to?
Yeah. So
everything transfer over somehow then?
So it's complicated. Yeah. So if I naively take the algorithm I described here, but I add Levy innovations and then still accept or reject, my acceptance rates will degenerate much more quickly. Actually, we have some calculations like that. For the continuous time process, you can sometimes show nice things. My understanding is that finding good ways of discretizing those that retain the properties you would like is far from a solved problem, let's say. The idea of processes which might be able to move more quickly in some directions to sort of equilibrate nicely, that has been done in different contexts. I would say for sort of piecewise deterministic processes, that's one of the appealing settings there, where you can sort of ballistically come down from it.
So is the issue that if you have something which is heavy tails, you're saying that if you sample it wrong initially, then you need to get to the middle? I thought it would be that somehow you need to get out to the tail.
So it's both. Yeah. It makes sense that in terms of exploring it, you need to see both sides. But it's a bit of a heuristic in some ways, but I think it...
And my other question was, so you're saying that you really gave some examples of large sets which have a small boundary. Would you be able to just say that again? What the simplest test in 2D, what distribution would you get, and what set would you pick?
So sorry, what's the question?
So you're saying that you have these problem sets, so these ones which have a large sort of mass but a very small boundary. They're hard to sort of get out of.
Yeah.
So what's an example of that? So it's Cauchy or something with like heavy tails, and are you taking products of that?
Yeah, so I can't remember off the top of my head how the extremal sets look in those cases, but I think they can be quite weird in the sense that the potential associated to a Cauchy measure is non-convex, and sort of taking a direct sum of those things as dimension grows gives you a very weird function in some ways. And so the idea that a sort of half space will be extremal there is a bit less obvious somehow. But yeah, I don't have excellent intuition off the top of my head.
So here, reversibility is an important thing to make these isoperimetry conductance arguments. And for instance, with spectral arguments, something which sometimes works with Markov chains which are not reversible but skew reversible, so that the agent is to apply the reversible results to like I do n instead of p and then n instead of p star, and I've tried to do that with this. I have never obtained anything useful. Do you know things in this direction?
So are people successfully using that idea?
Yeah, I more generally used conductance arguments for non-reversible chains.
Yeah. Not directly, but I think the argument makes a lot of sense. I mean, people certainly use conductance methods for studying HMC, which of course is a bit on the boundary somehow. But you can say, how close do I need to start the two chains such that if I pick a velocity, I can couple them well. And you can have nice conductance type arguments there, but I think it's not exactly the same as what you say.
So is that the same conductance and isoperimetry, or is that? Can you explain that?
Yeah. So
is it exactly the same, or just?
So in a way, if I go back to so if I go back to the isoperimetry, you're controlling the boundary of the set in terms of the mass of the set. The Markov chain version of that looks as follows. Is that chalk? So for a Markov chain, the notion of a boundary is something like the following. It's, so again, with a set A that we care about, right? We integrate over A and its complement. This guy here, okay? And so what we want to say is that this is...
So y is outside of A, is that the same?
Yes, exactly. So at stationarity, what's the chance that I start in A and I leave it again?
Exactly.
And so that would be sort of an isoperimetric inequality for a Markov chain. And indeed, when we do the analysis, we're looking at things like this.
Okay. In view of time, thanks to Sam again.